right. We'll keep this nice and short, but I realize by now you probably want to head to the reception, have a cold drink. So we're going to give a few more insights. Thijs gave some insights into Sophion this morning, and I'm going to give a little bit more details, make it short and sweet, so we can get Anissa up here and talk about some of the key scientific projects that we are currently dabbling in. So let's get going. As Thijs mentioned this morning, we have been investing a lot in ion channels the last 12 months since our last ICMS here in Japan. And I'm going to dive into some of the details. One of the things we've been doing is increasing our staff with about 20 people, both in the front line and in R&D and science, to about 110 people today. So we've really been scaling up to better support you guys. We've also moved to a new facility in Denmark, creating more lab space, more space for production, increasing our quality, etc. So, and giving our teams a better working environment. And regionally, we have been investing in more frontline staff. And also here in Japan, we are building, again, Thijs mentioned it this morning, a new facility with a better lab, with a better work environment for our people. So we're doing a lot to come closer to you guys, a lot to build the right facilities to support the growing interest in ion channels. All the people working in the front line in Sophion are, part of a lot of meetings, a lot of events, and including our scientists around the world are doing a lot of collaborations. The last 12 months we did more than 10 collaborations across the company. We contributed to more than 85 publications. We hosted 3 ICMSs, which is also a big commitment on our side, with more than around 400 participants coming globally. We attended more than 90 conferences within primarily ion channel field. And then we also invited a lot of collaboration through research grants and through travel grants. So it's been quite a busy year for us as well. We are also developing new technologies, new offerings, constantly focusing on providing relevant technology, relevant features, relevant stuff to our partners, our customers. Some of the things that are really interesting for us is we have done more on cloud-based integration. We've also looked at data from more than 20 years of Sophion automated patch clamping, where I was discussing this with some of you at lunch. Quite interesting to look into that and see how we can use that going forward. We've done several improvements on our software and hardware platforms, including launching a new adaptive current clamp feature that I'm sure Anissa will touch on. Finally, we have made significant improvements to the Q-Patch Compact. I know many of you have seen the smaller device we have out there that we essentially launched a few years back. And now we have improved it with temperature control, light guidance, and other cool things that makes it more easy to operate and improves the science. And then finally, on my end, a few words on all the things that we are doing internally and with our science and R&D teams to expand on biology and research projects. And This is obviously something that is at the core of Sophion, at the core of what we like to spend time on. And to expand further on these exciting fields that we have went into, I would like to invite Anissa on stage to dive into more of the details. Thanks for listening. Anissa?
Okay, can you hear me well? Good. So what we have been doing for the past year and where we are going, this is what I'm going to talk about today. So the mission of Sophion is actually to use our R&D department to develop innovative support for the ion channel community. So we have a big R&D department that consists of hardware, software, and biology, and we are working all together, but also with the ion channel community to develop different technologies to answer different answers on the scientific environment. So to do that, we have different engagement models that I would like to talk a little bit about and that can be very beneficial, especially for the academic world. So Michel, but also Thijs, they have talked a little bit about grants. So we have research grants, we have travel grants, now we have instrument grants that we are offering to different academic lab for them to have access to our technology and to use a higher throughput electrophysiology platform to use in their own electrophysiology projects. We have been involved in a lot of different research collaborations and academic partnerships, but this is also mainly, we have interest in a lot of different environments and questions. And sometimes in our own lab, we don't have access to some biology or different technologies that you guys have access to. So it's also in our interest to help and to support this ion channel community and to make progress in the science world of ion channels. We are doing a lot of different asset developments in-house, and I will talk a little bit about this as well. But we're also helping the ion channel community in different infrastructures, which can be CRO, pharma companies, but more recently, a lot in academia, thanks to our little device out there, to develop different cell lines, for example, but also different assays on ion channels that can be very special or very unknown or different projects like iPSCs, derived cells, for example. So I will talk I will give you sneak peeks of what we are doing in our R&D departments and what we have been working on with collaborations and partnerships. And I hope that will give you an idea of what we have been doing at Sophion, but also where we're going and how we would like to improve the scientific world in these ion channel communities. And the first thing is the neuron program. So the past year, we have two bright research scientists at Sophion that have developed this neuron program. And the goal of this neuron program, this mission of this neuron program is how we can use the automated patch clamp platforms in the neuroscience research. We know that the neuroscience research and the neuron recordings are quite challenging, I would say, especially in primary cells, for example. So that was the whole goal. How can we take the neuroscience research and make it more reproducible by developing a neuro program at Sophion? And to do that, we have had a lot of partnerships. So we collaborate with different big companies that provide us iPSCs-derived neurons from different brain regions. It can be motor neurons, DRG neurons, cortical neurons as well. And you can probably recognize Anatomics, CDI, Brain Excel. And recently, we have also been collaborating a lot with academic labs, especially the University of Copenhagen, but also Thermo Fisher, that is actually providing frozen primary rat cells to Sophion for us to develop assays on automated patch clamp systems. The main challenge that we have when we work with this kind of cell lines is the fact that we have to take cells that like to be connected together to a single cell suspension that we can use on our automated patch clamp platforms. So we have been developing a lot of those programs and protocols and assays to make sure that we can adapt to this neuroscience research. And as you can see here, of course, we have been able to record many of the voltage-gated ion channels, but we are also able to record ligand-gated ion channels that are quite important in neuroscience research, such as GABA or AMPA receptors. But we also know that those kind of ligand-gated ion channels, they can be challenging, especially when we talk about fast-activating ion channels, such as AMPA receptors or kainate receptors. So one of the things that we have, we developed that a little bit earlier, but we are going back on this field, is actually the light stimulation electrophysiology recordings. And we know that optogenetics is a great tool. We have seen a couple of presentations this morning, for example, talking about this, and that can really improve the temporal resolution. So a few years back, we actually developed what we call the OptoCube, and this is our biggest machine. This is our high throughput system that can record 384 cells in parallel. And we use that to develop this light stimulation, so this optical modulation of ion channels, but by coupling it with electrophysiological recordings. And we use that a lot to do optopharmacology, better temporal resolutions for ligand-gated ion channels like GABA. And recently, our R&D team have tried to and succeeded to implement this optical modulation into our smallest device that you have seen outside the Q-Patch Compact. And here you can see the preliminary results that we have had a couple of months ago, where we use this Q-Patch Compact with optical modulation with this cage GABA that we call Ruby GABA. And you can see some of the traces right here. So we have worked a lot on neurons and neuroscience. It is a big field for ion channels. But of course, this is not the only type of cells that we have been working on that are more difficult than the stable cell lines that we have masterized for the past 20 years. And one of those are actually cardiomyocytes. But of course, when we talk about cardiomyocytes, also we have to talk a little bit about organoids. And over the past, I think now 2 years, 2.5, we also focused a lot on iPSC-derived cardiomyocytes. I think we gain a lot of knowledge and expertise on how we can use iPSC-derived cardiomyocytes into automated patch clamp system, and we know how difficult those cells can be. They are challenging because they are derived from humans, but again, they like to be all together and beat together and be this big sheet of cardiomyocytes. So again, we developed multiple protocols in with some partners like NCardia or again CDI, but also some academic institutions like the University of Göttingen to make sure that we can keep the integrity of the cell membrane and the ion channel expression when we go from a monolayer of cells to a single cell suspension. We have been able to get a very good success rate on our different systems where we can record the different ion channels expressed in those cardiac cells from sodium, potassium, calcium, but also action potential. As we have seen in the previous talk, but as you probably know when you work with this kind of stem cell lines, the main challenge is the immaturity phenotype of those cells. Those iPSC-derived cardiomyocytes, even though they are a great tool for personalized medicine, for example, or for a more physiological assay, they also are very immature. Some of those cells, they actually express some ion channels that they shouldn't, but they are also lacking the expression of some ion channels that they should express. And all of this, it results in a huge variability for these electrophysiological recordings. So we have seen a lot of variability from batch to batch, from vendor to vendor, and this makes those kind of studies quite difficult. So at Sophion, we have decided to overcome this challenge by using our hardware team to develop a feature that is called adaptive current clamp. So this kind of action potentials that you can see, this is a lot of cells that are expressing this kind of action potentials. Very steep, the resting membrane potential is very depolarized, and everything is due to the fact that those cells are immature. So to overcome those kind of challenges that we have when we work with stem cell lines, the hardware team developed a tool that will measure individual resting membrane potential for each cell and what is the current that we need to inject to bring them to a better, more physiological resting membrane potential. So the system in the different formats, the 8-channel, the 48-channel, the 384-channel, will just measure and record the value, individual values, and then they will apply this value to just bring the cells back to a more physiological state that will be closer to primary cells. And this is what you get at the end. So this is the exact same cells that when you had a very steep depolarized ion channels, and now you get this primary cell-like ion channels that you can use to do some pharmacology, for example. So I talked about now single cells, and recently we had the chance to work with the medical school at Hannover in Germany, and this lab is actually experts in the massive production of iPSCs cardiomyocytes, but in tank bioreactors. So they are just using those iPSCs, they are cardiomyocytes, can be physiological, but also maybe expressing a disease. And they use them for expansion and maturation, but also differentiation into these tank bioreactors, which they form organoids, like those spheroids that are multiple cells in one tissue. So it's more like a tissue-like. So they came from Germany by train to Sophion and with the bioreactors, and we wanted to see what we could do with those cells. There are two main parameters that can be used to assess the functionality of iPSCs cardiomyocytes, cardiomyocytes in general, and one of them is contractility. This is at the tissue level. And at Sophion, of course, we are also interested in the electrophysiological part of this characterization, functional characterization. And this is by doing single cell recordings. So we took those organoids, we actually dissociate them. So we also created protocols for that. And then we were able to actually, correlate those tissue recordings with the single cell recordings. Cardiomyocytes are not the only cells that people are using for organoids. So recently, we launched the collaborations with the University of Luxembourg to use midbrain organoids with the lab right there do has actually a Q-patch compact. So they develop those organoids. They just culture them for days, like almost 70 days. And then they are, at least in their own lab, they're using different technology to assess the tissue properties. So they are using microarray assays, so this MEA, but also the patch clamp, the manual patch clamp with the sharp electrodes to measure what's happening into the tissue. And now the goal for all of us is to, again, develop a protocol and assays that we can take those organoids and use these tissue recordings and correlate them with the single cell recordings into the Q-patch compact. And finally, so the last part is what we call at Sophion special cell lines. This is cell lines that are just different from everything that we have been doing so far, so stable cell lines, but also iPSCs and primary cells. We have been investing a lot because the interest has been growing into the ion channel research field. And we would like to give the support, the necessary support to improve the reproducibility and decrease the variability when we use high throughput automated patch clamp. So the first spatial cell line that we have been investing in so far, it's red blood cells. So we actually have a PhD student that works at Sophion. The goal, and the mission of this PhD student is to be able to use those red blood cells and put them on our automated patch clamp platforms to record the different ion channels expressed by the red blood cells. The second spatial cell lines are cell organelles. We know this is a hot topic, so of course we want to jump into this, the boat and be ready to support any lab that are doing any organelles. And right now we are collaborating with different partners to develop those kind of assays. Obviously, the challenge is the size. The size, but also the flexibility of the membrane. We know that red blood cells, and this is the main role of red blood cells, is to just be very elastic to be able to go from vasoconstriction to vasodilatation. And then we also have the cell organelles that are way smaller than a cell. So how can we overcome this challenge by doing electrophysiology on an automated patch clamp system? And to do so, we have a great biomaterials consumable team that develop different kind of consumables to adapt to the cell to adapt to the size of those cells. And we now have this, what we call the small hole consumables, which is smaller than what we use for hex cell lines or iPSC-derived cell lines, and so on. So just to jump a little bit into the very preliminary data that we have from this project, here this is the red blood cell project. Red blood cells are expressing many, many different ion channels, NMDA receptors, but the most known, I would say, the most famous one is piezo-1, obviously, and Gardos. So the goal, we are actually partnering with Novo Nordisk, but also Rigs Hospital, sorry for the Danish pronunciation, in Denmark. And the goal is to develop an assay on those small hole consumables to record ion channels in red blood cells, and then use the blood from diseased patients that have different mutations on those Gardos and piezo-1 channels, and to see if we can understand better what's happening at the functional level of ion channels. And right here, this is piezo-1 recording. So we're actually using the cube. So the cube is our biggest machine. And the cool thing with the cube is that you can modulate the speed of the liquid dispense, which will create what we call the shear stress. And the shear stress is just a pressure against the cells that is resulted with the speed of the liquid addition, and that will activate piezo-1. And here this is Gardos, which is calcium-activated potassium channels as well. Both of them are being recording in red blood cells on our Cube 384. And finally, we don't have any results yet. We have been working on it, but this is quite challenging, but this is also why we are here. And we have a three-way collaborations to develop what we call the lysopatch. So this is automated patch clamp system to do electrophysiological recordings into lysosomes. And to do so, we're partnering with one of a long-term partner called Sophion Bioscience, who are doing all the high throughput recordings on the cube, and with a French company called Oraya. And this is a very small company that just came out I think 2 years ago, and they actually specialize into the production, the massive production of organelles that we could use for this specific project. So again, please remember, we are always open for collaborations, especially with academics that have crazy projects in mind. We are offering travel, but also research grants for students, for postdocs, for them to come to Sophion, have access to our technology, but also to traveling to different ICMS and conferences. And recently, we also launched this instrument grant where you can apply when you are an academic lab. You can just apply to us with your own project, and then we will place an instrument into your own lab that you can keep between 6 and 12 months to just enhance the ion channels research with high throughput electrophysiology. So please scan the QR code, apply. We will review every project that you want to collaborate with us and use our technology with us. So thank you very much for your attention. Thank you for being here. Thank you to the Japanese team, and I'm sure we will have a great reception. So thank you again.
I don't know if you'll entertain some questions, if there's any questions from the audience. It's a fascinating development. Thank you. Yeah. All right, if not, I would like to...
There's a question.
How can you do work while going to 90 meetings?
Tell that to my boss someday. No, obviously that's why we are investing in frontline people. So we want, again, it's so vital for us to be close to the science community out there by deploying and participating resources into those meetings. We're getting, the latest and greatest insights. So as also Anissa was mentioning here, a lot of these collaborations start, at events like this or other events.
All right, so I would like to...
There's a question right here.
More question.
Of course.
That's important, yeah. All right, so I'd like to, on behalf of all the speakers and the audience, to thank the organizer for this really wonderful meeting this first day, and we'll have continued next day meeting. And also, I would like to thank all the speakers for this session for giving wonderful talks. Thank you.